Hello guys, this is Paul McWhorter with TopTechBoy.com, and we are here today with lesson number 18 in our incredible new tutorial series where you're teaching the robots who's going to be boss. I'm going to need you to pour yourself a nice big cup of strong black coffee. That would be hot coffee, no sugar, no sweeteners, none needed. I am also going to need you to get out your robotics gear. And as you're getting your gear out, as always, I want to give a shout out to you guys who are helping me out over at Patreon. It is your encouragement and your support that keeps this great content coming. You guys that are not helping out yet, look down in the description below. There is a link over to my Patreon account. Think about hopping on over there and hooking a brother up. But enough of this shameless self-promotion. Let's jump in and let's talk about what we are going to learn today. What we're going to do is we are going to look at my solution to the homework assignment that I gave you in lesson number 17. So let's just review a little bit of where we are on the old Elegoo Smart Car. I believe it was in lesson number 15 we got to the point that we could control the smart car using Bluetooth on a smartphone. And it was really neat because we could program the velocity and we could program the desired distance and then hit go and it would go. We could turn it right, we could turn it left, or we could go backwards. So pretty capable based on lesson number 15. But then we wanted to start moving towards obstacle detection and collision avoidance. And so in lesson number 16 and lesson number 17, we turned on the old HCSR04 ultrasonic sensor, and we kind of developed an ability to just sort of send a ping out, look for it to come back, and then understand if there was an obstacle in front of us, and if there was, how far away was it. But the lessons 16 and 17, the car wasn't running or doing anything. You could just kind of go out and see how far the car was, how far the obstacle was away. Well, what I assigned you was I assigned you the assignment of going back to lesson number 15 and then incorporating that ultrasonic sensor, that object detection or obstacle detection capability into your program from lesson number 15. And what the assignment was to constantly be looking out in front of the car, and if there was an obstacle, to stop the car and kind of pause your mission until the obstacle was removed and then continue the mission. Okay, this turned out to be quite a bit harder than what I had anticipated it, because you had to not only keep track of how far you've gone, but you got to keep track of the time when the motors aren't running so that after the obstacle is removed, you can continue on with your mission. Now, if you did something simple like just looking out and there was ever an obstacle in front of you, you just stop. That's a little bit easier, but if you want to take it all the way to when the obstacle is removed to continue the mission and reach your target destination, that turned out to be a little bit harder than what I had anticipated. I actually had to spend a couple of days to get the algorithm working just right, and I also ran into a couple of glitches along the way, but I figured those out, and I'm going to share those with you. I'm not sure if you ran into some of these same difficulties that I did. But what I am going to need you to do is I am going to need you to get out a fresh new Arduino IDE, always starting with bare minimum. And we want to go ahead and we want to start with that lesson that we left off with in number 15. So we will go to the most excellent www.toptechboy.com, and you want to do a search on robotics training lesson number 15 in case you didn't save that. You can come down here and click on the two little pages, right mouse click and copy. And then we will come back to our Arduino IDE. We will Control A to select everything, Control V to paste what we just copied. And now we should be set up to go back and be able to control the car with the smartphone. But as I said, we want to detect objects. And so we're going to go ahead and take advantage of the work that we already did. We don't need to start from scratch every time. We're going to go to the most excellent robotic training lesson number 17. And what we want is we want these two functions down here that were in that software, the ping time function and the float measure distance function. So we're just going to grab those two. We're not going to grab everything else. Those are just the two things that we need. So I'm going to get starting with the int function ping time. I'm going to copy that and the float function measure distance. And then we're going to come over here and we're going to paste that after the other code. So these are going to be two functions that we tack on to the end of the code. So this isn't anything new. If you don't understand this, go back and look at lesson number 17 and go back and look at lesson number 15 because I explained all this stuff back then. Okay, now we are going to need to set up a couple of variables. Remember, we have our trig pin and we have our echo pin. And so we need to go up to the top and go ahead and set those up because, yes, we will need to turn those on. So I'm going to go to the top of the code. And I'm going to make an int for the trig pin, trig. And that is connected to A5. Again, that is hardwired into the Elegoo Smart Car, that the ultrasonic sensor, the trigger pin, is connected to the Arduino A5, and the int echo is connected to A4. I mentioned in the earlier lessons, I really don't like how they hardwired a sensor into the analog in pins. I would have preferred to do that a little bit differently, but that's how they did it, so that's what we're going to go with. Now we will need to, the one other thing we need to do to add to this is we need to go to our void setup and we need to go ahead and do our pin modes. And so if you remember from the earlier lesson, the trig pin is an output like that, and then pin mode, and the echo pin is an input. So I think that should all work at this point. I think that's everything we need. You know what I think I'm going to do? I think we're going to go ahead and download that code just to make sure that we haven't broken anything. And always a reminder, you've got to take the little Bluetooth module out when you are downloading the program. So let's go ahead and let's see if we broke anything in this. I don't think that didn't look like. Let's make sure I've got the... Well, that is sort of strange. I've got like 3,11s. So I'm going to try this one more time. Okay, I think it's going this time. That was a little strange why it's seeing all those COM ports over and over. But it does look like that it compiled properly, and it does look like it downloaded. So basically, I think what that's saying is I haven't broken anything. Okay, now just to remind you, we've got a lot of different functions. We've got a forward function, we've got a backwards function, we've got a turn left function and a turn right function that we can make this car do. We're going to do the collision avoidance, the obstacle detection, and the collision avoidance going forward, because of course this sensor can't see behind it, so it wouldn't make any sense doing it backwards. But just when it's going forward, it's going to make sure that there's nothing there that it's going to run into, and if there is something there, it needs to stop. And so that would actually be this G function. Remember, G on our little smartphone, on the Bluetooth program on the smartphone, G makes it go forward. And so that calls the function forward. And so that forward function is going to be the function that we are going to be working with today. So let's see if we can find that forward function, which of course is always hard to do when it's in the middle of things, but here it is. Okay, now let's look at how we did this the first time. We pass it the distance that we want to go and the velocity that we want to go at, And then it calculates, because we did all of those calibrations. Remember all those calibrations that we did? It calculates the time that you need to leave the motors on in order to go that distance, because you can kind of think of distance is rate times time. So time is distance divided by rate, and so this is the distance and this is the rate, and then we multiply by 1,000, so everything is working in milliseconds, because our various Arduino functions wants to operate in milliseconds, so we convert the time into milliseconds, so everybody's playing happily with the same unit. And then what we just do is we turn the motors on, and then we let the motors run for T time. Now that's great, but what is the problem? This is what is called blocking. That is when you get to this line of code, Arduino sits at that line of code for T milliseconds. You can't come in and give another command. And so imagine you needed to have the motors running for 9 seconds. T is 9. That means when you get to delay T, it's going to sit at that line of code for 9 seconds. So you can't be sending out pings. All right. So you can see that we are going to have to fundamentally kind of think about this differently to come up with a way to do the timing that is non-blocking. And that means is that as we're driving and as we're keeping track of time, as we are doing those things, we will be able to be checking for obstacles in front of us. And so we will need to do some adjustments. The first thing is we're going to have a lot of different times that we're keeping track of, because we're going to kind of keep track of how long have the motors been on, how long do we want the motors to be on, how long have the motors been off. And so we've got to be a little bit more precise in defining our variables. And so this T here that we were just calling T, I'm going to call that T target. That is our target value of time that we want to leave the motors on or running. And then I need to change this up here too, because that is also going to be T target. So T target is the amount of time that the motors should be on. Now, of course, we can't do this delay anymore. Okay, we can't do this delay anymore like that. And so what we're going to have to do is we're going to have to think of a different algorithm. Well, what I'm going to do is I'm going to say T target is how long we want the motors to be on. And I want to compare that with a new variable T on, which is how long at this point in time have the motors been on. So then I can compare T on, how long the motors have been running, with T target, how long we want them to be running. And so we're going to have to come back up here, and we're going to have to define another variable, which is going to be an int, and that is going to be T on, how long we have actually had them on. Okay, so we've got the T target and we have got the T on now. So those are two very, very important variables. I just realized something. I got to make one other little change here, and I'm sorry this is kind of an awkward time to do it, but I just remembered that down in this code that we had developed before to measure distance and to measure ping time, what I need to do is, instead of an int, when I take this off and just put it on the floor and there's nothing in front of it, that pulse in that it measures turns out to overflow the int. It's like bigger than 36,000 or whatever the maximum int is, and then with that you start getting unexpected results. So I need to make this an unsigned int, and since you're only using the positive numbers and not the negatives, you can have a much larger number without overflowing. Well, if I'm going to make that an unsigned int, then this function needs to also be an unsigned int. And the ping travel time needs to be an unsigned int. Okay. What I was finding is I would do that pulse in measurement, and if there wasn't anything in front of it, that ping was going way out, and it was gone for more than the 32,000 or the 36,000 or whatever microseconds, and therefore I was overflowing that variable. But with the unsigned int, I do believe that we will have a large enough variable that we won't have that problem anymore. So ping time, the function needs to be made an unsigned int. Ping travel time, the variable needs to be made an unsigned int. And then down here, the ping travel time needs to be an unsigned int, just to make sure that we don't overflow that variable. But I have digressed, and we need to come back up to our most excellent forward function. So now what we want to do is we want to only leave the motors on, not for the t target amount of time, but we want to constantly kind of just be leaving it on until t on is equal to t target. So the way we're going to do that is we're going to say while the variable t on is less than or equal to the variable t target. Okay, we're just going to have a little while loop here, and what this while loop is going to do is and I should not have put that closed there, it closed it for me. What it's going to do is it's just going to kind of hang there. It's going to just kind of hang there. So as long as t on is less than t target, it just sort of sits in that while loop. And then when t on reaches t target, we've run it long enough, we've gone far enough, we drop out of the while loop and we turn the car off. Okay, so as long as how long we've been on is less than or equal to what our target is, we just kind of sit and wait. Well, if we're going to do that, we've got to define what t on is. Okay, we've got to define what t on is. Well, we've got to figure out, when did we turn the motors on? T start is when we turn the motors on. So we need to go out and grab the system time here. And so when you do a millis, you're just looking and kind of asking it from the system clock, what is the present time? And that's actually the number of milliseconds since you started running this program. And so it's sort of like a continually incrementing system time. So we're going to grab the time here. And so t start now is the system time at which we turn the motors on. Okay, so that is the start time. Well, then down here, before we go into this while loop, we need to actually measure t on. Well, what is t on going to be? It's going to be the present system time minus the t start. Right? Now you might be asking it, oh, I am not putting my semicolons in, am I? Okay. You might ask, well, why do we need to do this? Because we've just turned the motors on. The reason you have to do it is in this line of code, it wants to compare t on to t target, and so you've got to have a value for t on. Certainly the first time through it's going to come into this, but you've got to have the variable defined, and it really does make sense. How long have the motors been on? Well, the present start time, the present system time minus when you turn the motors on. So like if you turned them on at the 2-minute time frame and now it's 2 minutes and 10 seconds, well, 2 minutes and 10 seconds minus 2 minutes, the motors have been on for seconds. So hopefully that kind of makes sense. Okay, now we're going to come down in this, and once we get in this loop, we've got to constantly update t on, or this would just hang up here forever. So what we have to do is we have to constantly update t on. And so t on is equal to millis, the present time, minus t start. T start. All right. Now, at this point, the program should, I do believe, pretty much do exactly what it had done before. Okay, this is just a fancy way of doing the delay. It's a fancy way of doing the delay. As long as T on is less than T target, it's going to sit here just measuring T on, and then when T on gets to T target, I'll put less than or equal to, when T on gets to T target, then you're going to drop out and you're going to stop the car. Does this make sense? I sure hope it does. Okay, now what we've also got to do is, inside of this while loop, the whole reason for doing this is, do we have an obstacle? Okay, so we need to see, do we have an obstacle? And so down here, I'm going to see if I have an obstacle. And so how am I going to do that? Well, I'm going to say distance to the target is equal to measure distance. Okay, what is measured distance? Measured distance is that function that we just added down here that measures the distance and then returns the distance, and it returns the distance as a float. So when we say d target is equal to measured distance, then at this point we're going to know if there is an obstacle in front of us, and if there is, how far off it is. Well, if we are going to do that, we had better add a new variable. We better declare this variable d target, and since it's returning a float, we should declare it as a float. So I'm going to say float d target up here. Okay, so now we have declared that variable. So while we're in this while loop, and in this while loop the car's driving, trying to get to its target destination, its target distance, which we're measuring as a target time, we're constantly measuring distance, okay, to the obstacle. We're constantly measuring distance to the obstacle. Well, now, if we do in fact see an obstacle, what do we want to do? We want to stop the car. And so what we're going to do is we're going to say while d target is less than or equal to 12 inches. And so this is saying I'm going to get within 12 inches of a target, and then of an obstacle, and I am going to stop. Within 12 inches of a obstacle, I'm going to stop. I think d target, I think I'm going to call this d obstacle. Okay, the distance to the obstacle. That was kind of a poor choice of a variable, distance to the obstacle, because that's what I'm measuring. I'm measuring if there's an obstacle, and if there is, how far it is to that obstacle. All right, so we're going to come down here and we're going to say if the distance to an obstacle is less than or equal to 12, and then I better measure the distance to the obstacle, because it's not a target, it's an obstacle. Okay, so while the distance to the obstacle is less than or equal to 12, what am I going to want to do? Okay, well, there's going to be several things that I want to do. The first is I want to stop car. And right, we already have a function called stop car, and it just turns the motors off. All right. Now the problem is, if we just left it like this, once it got into here and the distance to the obstacle is less than 12 and it stops the car, it's going to be hung here forever. There's no way for it to realize that the obstacle has been moved. So the other thing that we want to do in here, we want to be measuring the distance to the obstacle, and that's going to be equal to measure distance again. Okay, and this is like, you really got to pay attention to this, because you put up together a great while loop here, but you got to make sure that you're doing something inside the while loop that'll release it, that'll allow you to get out of it if the conditions warrant. For this, it's measuring the distance to the obstacle inside of the while loop. Okay, so now there's a couple of other things that we want to do. We've got to, at this point, actually keep track that, yeah, the car was stopped, because once we get out of this pause for the obstacle, when you get out of it, the rest of the program needs to know that you had actually stopped the car. And so what we need to do is kind of set a flag. So I'm going to say, if I get in here, I want to say car blocked is equal to true. Okay, car blocked is equal to true. And that means after I fall out of this, the program knows, hey guys, you got to do some bookkeeping because the car stopped. And if I'm going to use this Boolean variable, I'm going to have to declare it up here. So up here, we're going to say a Boolean, which is going to be car stopped. And initially the, was it car blocked or car stopped? I might have car blocked. Okay. So this should be, was the car ever blocked? Okay, and that is going to be a Boolean variable. And initially when we set it up, it's never been blocked. So we'll just set it initially to false, saying, hey, when you start out, there was no obstacle. So just set the car has never been blocked as you enter this function. But if there is an obstacle less than 12 inches away, less than or equal to 12 inches away, you've got to notify the system that, hey, the car was blocked. Why? Because when the car is blocked, okay, the motors are going to stop, and now we've got to adjust that variable. We've got to adjust that variable T on because the motor was off for part of that time. So I think that if I show you this, it's going to make sense. So actually, if I come up here to T on, the amount of time that the motors is on is going to be the present time minus the start time, but then also we're going to have to subtract the T stopped. Okay, so as we're going through here, something blocks the car stops. Now we've got to keep track of that stop time as well. So T on is going to be the present amount of milliseconds minus when we started it, and then minus how long was it stopped for the obstacle. Okay, does that make sense? Well, and I think, let's see here. Okay, so we do it here, and then also we need to do it here, minus T stopped. And so always now T on is going to be the actual amount of time that the motors were running, and it's going to keep track of that little while loop where the motors were turned off. Now, if we're going to do that, we need to set up a variable for T stopped. And so this is going to come up here, and we'll put another variable in, an int T stopped. And initially, it hasn't stopped, and so the initial stop time is going to be 0. All right. And the reason we have to put a variable in was, first of all, because T stopped is 0, and then when you get down here, you won't crash, that there's actually a value to put in for T stop. There's actually a value to put in for T stop. But now if we're going to use this stop time, this conceptual stop time, we've got to define it. And so how long was it stopped? Well, this is right before it stopped, so I'm going to say T1 is equal to millis, the system time. Okay. And then after this, I'm going to say T2 is equal to millis, like that. Okay, does that make sense? So as I'm going into this stop, right before I go into it, I grab a system time, and then right after I come out of it, I grab a system time as well. Okay, so now I've got the time right before I hit the obstacle while loop and right after I hit the obstacle while loop. Well, now what do I know? Well, I know that I only need to calculate T stopped if it actually did stop. So that would be if car blocked equal true. Okay, so If the car did stop, then I need to calculate a stop time. Now, why would I not just calculate the stop time here? Because if there was not an obstacle, then this never happened, and therefore there was no stop time. But if I calculate the stop time even when it hadn't stopped, then you're going to kind of have this error that starts creeping in. So you only want to calculate stop time. You only want to calculate stop time if the car actually stopped. And that would be if the car was blocked. So if the car was blocked, then T stopped is going to be equal to T stopped plus T2 minus T1. All right. Now you might have been thinking, why not just make T stopped T2 minus T1, because that was how long it was stopped. But what you got to think is, what if I put a blockage in it and then waited and took it out and then put it back? Well, then you have a cumulative stop time, the amount of time it was stopped the first time and the amount of time it was stopped the second time. So you've got to add the stop time. You've got to add the stop time to whatever the stop time already was. And then that's another reason why we have to initialize the whole thing to 0. Does that make sense? I'm just thinking about, what if you encountered 2 obstacles? This algorithm will work in that case. Okay, now we don't want it the next time. Once the obstacle is removed, we don't want it the next time through to come into this car block thing, because the car is not blocked anymore at this point. Once we get into this, we want to go ahead and say we've done our bookkeeping, we've adjusted our variable, so now we want to say that car blocked is equal to false, because we've done everything in this loop and we only want to do it after we've had a blockage. Now we've taken care of that blockage, and so we want to say car blocked is equal to false, so it doesn't drop into this loop every time through. Okay, and so what do we want to do in car blocked? Well, we want to say that keep track of the T stopped, and we want to keep say that the car is not blocked anymore. And then what else do we want to do? We remove the barrier. It sees it's clear. Got to turn the motors back on. And so what we will do is we will get these 4 lines of code that turn the motor on. Okay, and then we will come down here and we will turn the motors back on. Okay, and then it will just continue looping and continuing to let T on get bigger and bigger and bigger until now, when the T on is less than or equal to T target, then the car stops. It's like at that point, mission accomplished. But I am keeping track of the T on, and I am taking into account that if the car stops, I need to subtract that amount of time that the car was stopped from T on. So I think I am doing all of my bookkeeping correctly here. I hope it makes sense, guys. If it doesn't make sense, back up and watch this again. It's like you've got to keep track of the amount of time the car was off, and you got to subtract that from your T on time, and that way you will in fact reach the designated mission target for distance. Okay, what are the chances this is going to work? Man, we have done a lot of code. I will need you to hold your breath on this one. Let's see. We come in. I lost my function. Where am I? I was moving around and I kind of lost my forward function. I think this is it. Okay, so here it is. And so if the car is blocked, we turn the we update our stop time. We flip our car block flag back to false, and then we turn our motors on. And then after this if statement, after this if statement, then we continue on with our normal mission. Okay, I need you to hold your breath. Oh, T-start not declared in this scope. Okay, did I not do a T-start? All right, I did not declare T-start up here. I thought I had. Int T-start. All right, and we don't have to put a value there because it will, here in the next couple of lines of code, it will grab that. All right. Oh, T1 and T2 I didn't declare. I think the real problem is you guys are not holding your breath. So I need to come up here and I need to say int T1 and I need to say int T2. And I don't need to give it values because the first time through the loop it's going to grab the system time before the loop and after the loop, and so they'll always have values. Please, everyone, hold your breath. Yes, yes. Boom, we get the happy little blue bar, no errors. And so at this point, I think the thing actually ran. I mean, it actually compiled, it actually downloaded. Now, whether it works or not, I don't know. And so what we're going to do is here, let's see if I can get a nice view for you. We need to now put our Bluetooth module back in. Okay. And then I want you to kind of see what I am doing with the phone. So I am going to go to our Elegoo program. Remember, we have our little Elegoo Smart Car. And so we're going to do that. And then we're going to try to get the Bluetooth connected. And so I will hit that little Bluetooth connect icon. Okay, it is trying to connect. And with Bluetooth, of course, you always, there it is. Okay, so that looks good. All right, so let's see if I can get something. I wonder if I can actually just kind of look down on this. Pardon me while I try to get something cool for you to look at. Okay, I think you could almost read that, couldn't you? Okay, so what I'm going to do is I'm going to try to focus that for you. Give me just a second to give you a little better focus. Okay, that looks pretty good on the focus, doesn't it? Okay, and then I will unplug the USB cable. And I didn't have the car turned on, so I'll have to connect again. Okay, so it's trying to connect. I don't know why Bluetooth pairing sometimes goes fast and sometimes not so fast. Okay, there it is. So now it's paired. And so now I'm just going to say a distance of 5, and you can see I have it up here without any obstacles, and then I'm going to say go, and then we'll just kind of count how long. 1, 2, 3, 4, 5, 6. Okay, about 6 seconds. Okay, about 6 seconds. So let's go again. 1, 2, 3. Now you see what I've done is I've given it an obstacle, so it stopped after about 3 seconds because of the obstacle. And now let's take the obstacle away. 1, 2, 3. Okay, do you see? Let me see if I can make that a little bit clearer. So it takes about 6 seconds to go the 5 feet. All right. But in the middle of it, I'm going to put an obstacle, and I'll leave that obstacle for some period of time. And when I take it away, then it should finish the mission. We're just trying to see if this sort of works. Okay. 1, 2, 3. Okay, the obstacle is there. It's stopped. We could say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. When I take it away, we should see it about another 3 seconds, right? 1, 2, 3. Okay, A little bit more than that didn't count perfectly. But conceptually, it seems like this thing is working, right? That if there is an obstacle, it stops. It keeps track of how long it is stopped. And then once the obstacle is removed, it continues on with its mission to the desired location. So it actually seems like that works. And so I think at this point, we should go over to the test track and we should turn on the most excellent RoboCam. We're going to turn on RoboCam and we're going to go out there and see if we can make this thing work. And hopefully you can hear me when I'm out there. All right, guys, let's see if we got this thing working. All right, the first thing I'm going to do is, I guess I need to get down here a little lower. The first thing let's do, let's just see if this is going to go. Can you see that? I think you can. Let's see if this is just going to go roughly the 6 feet that we, or the 5 feet that we had programmed it at. So I'm going to say D5, and now I'm going to say go. 1, 2, 3, 4, 5. Okay, it went the 5 feet. I'm going to say reverse. Shazam! At least we didn't break it. It seems to be working. Now, let's see. I'm going to put the obstacle there. Well, I'm going to put the obstacle further away so it'll go a little ways, okay? And now I'm going to say go. Comes up, and it stops, all right? It sees the obstacle. Now, this didn't just kind of dumbly shut down. What this is doing is it's constantly in that while loop, and right, distance to the object is less than 12. Distance to the obstacle less than 12. It's sitting there, sitting there, sitting there. And now I take it away and it completes the mission. Boom! Did you see that? Now let's bring it back. Now, will it work with 2 obstacles? Will it work with 2 obstacles? So I'll put the obstacle here. Okay. And now I'm going to say go. Okay, it stopped because it sees the obstacle. All right, can it really keep track of stopping twice? So I'm going to move the obstacle further away, and now it stopped a second time. Now the question is, will it complete its proper, its proper 5-foot mission distance? So it's like 1, 2, about 3, and then it's going to go 4 and 5. And it went the right amount. And let's come back now. Shazam! Okay, I'm gonna go. I'm just gonna try something. I'm gonna go. Okay, and now I'm gonna do a right turn, and I'm gonna do a right turn, and now I'm gonna come back, going this way, and see if it'll. Yeah. Okay, you see, it stopped. And then I take it away, and it stops again. And I take it away, and it comes all the way back. Boom! Did you see that? All right, guys. All right, man. That was pretty slick. That was just pretty darn slick. Okay, I would say, guys, that we did what we set out to do, and that was to be able to complete the mission, that if there is an obstacle, stop for the obstacle. But if the obstacle is removed, then to continue to the mission destination, the distance for the mission destination. And that actually worked. And we were able to show 2 or 3 stops, and it was keeping track of things. And it was keeping track of things because we were really careful. Kind of a key thing here was that the stop time is not just the stop time. The stop time is how long it was stopped before, formerly, plus the new stop time. And that's kind of what lets you do multiple stops there. And also, initially, I tried to do this stuff up here in this initial loop, but there was no really good way to do it. You want it to stay there as long as there's an obstacle. When the obstacle is removed, then you come down and you update your stop time. Actually, like I say, this was a lot harder. This was a lot harder than what I thought it was going to be. Okay, this has been lesson number 18. As you usually have grown accustomed to, I need to give you homework for next week. What your homework for next week is, for a target like that box that I had, next week what I want you to do is, when you see the target, that there's an obstacle, I shouldn't call it a target, when you see an obstacle you should stop. Okay, now I want you to I think that maybe it might work a little better if you stop like 6 inches from the obstacle. So you see an obstacle, you stop at 6 inches. Now I want you to try to drive around it. Okay, I want you to try to drive around it. So what you could do is you could turn to the right, you could go a foot, you could turn to the left, and then go around it, and then continue your mission. All right. Now you're going to have to think a little bit. You're going to have to think a little bit about doing your bookkeeping, that, you know, as it's going around it, that is getting closer to the target. This isn't getting closer to the target. This isn't getting closer to the target. But when you're over here and go like this, that is getting closer to the target. So you're going to have to kind of take that into account on your on time, and you know, you're going to have to do a little bookkeeping like I did here. Okay guys, was anybody able to do this? Were any of you able to do this on your own? Were you able to at least do a little bit, like just go out and have it stop when there was an obstacle? And like I say, it was a little bit tricky, because if you were still stuck in the mindset of just doing a delay for time t or a delay for the on time, no way that you'd be able to get this to work, because that's a blocking function. So leave me a comment down below. Let me know who was able to do this. Let me know if anyone is still watching these lessons. Okay, I had done a lot of these robotic lessons, and then I got really overwhelmed here with my real job, and so I kind of paused for a little bit. I think several of you rightly were getting a little frustrated with me, because you guys were ready to get some more lessons and I wasn't delivering them. Is anybody still watching this series now? Okay, if you are watching, what was your luck? Were you able to do it without watching me? Were you at least able to kind of get it working without watching me? After watching me, have you been able to get it working? Has anybody at this point actually gotten it to do what I have shown here? Okay guys, I am having a whole lot of fun with this. I hope you guys are enjoying taking the lessons as much as I am making the lessons, and I will come back next week with the solution for the homework that I just gave you, and then we'll probably start adding some more bells and whistles to it after that. Alright guys, thanks a lot for tuning in. If you enjoyed this video, give us a thumbs up. Man, when you give us a thumbs up, it really helps me with the YouTube algorithms. What also helps me with the YouTube algorithms, if you would leave a comment down below, that increases the video engagement. And the more engagement I have, the better I do with the algorithms. And of course, share this with your friends, and subscribe to the channel if you haven't. Paul McWhorter from TopTechBoy.com. I will talk to you guys later.